Okay, in the previous lecture, we started to learn how to solve heat equations, basically. So remember, we were talking about heat equations. Of the form dt by dt is equal to d squared t by dx squared. Okay. So given the initial and boundary condition, we want to know how to solve these equations, these forms of equations. Okay. Now, the first method we learned is called the explicit method. Explicit finite difference method. Okay. The method was very simple. We basically approximated this equation of the form Ti L plus 1 minus L divided by delta T is equal to D times Ti plus 1 minus 2Ti plus Ti minus 1 divided by delta X squared. Okay, and then we in the explicit method, what we did was we basically assumed all these values are calculated at L. Okay. And if you recall, we had a computational element. So remember, we were actually going from the L to L plus 1 steps always. So if you assume this as my L step, this is my L plus 1 steps. So your computational molecule looks something like this. Okay, so we basically use previous values to compute my Ti L plus 1, and we also introduce another notation where I said I can call Ti L plus 1 as simply as Ti and Ti L as Pt. Okay. Now under that notation, I could write this as basically Ti minus Pti is equal by delta T is equal to D times Pti plus 1, everything in previous time. Okay. So these are the two notations we used, and they are interchangeable. Okay. This is Pti, interchangeable. Okay. Now, in this lecture, we are going to talk about a new method called implicit method. Okay. And so I'm going to define what is an implicit method and how to use implicit methods to solve these problems, and what are the advantages. We'll also we'll go on to discuss the advantages of using implicit method for this class of type of problems. Okay. So let's think about it. So again, we are solving. So let me rewrite it again. So let me push this up a bit. Okay, so our goal is to we are still with the same goal, solve. Using implicit method. And we'll, as a part of this actual solution procedure, as we start developing this procedure, I'll talk about what is the implicit method and what are the advantages of the implicit method, and so on and so forth. So we will evolve this lecture as we go along. Okay. So first, let me talk about implicit methods. What is the implicit method? Well, to do implicit method, my right hand side. My left hand side, which is dt by dt, there is no change. Okay. So I'm going to approximate dt by dt as exactly same as we did before. Okay. What did we do before? We said Ti L plus 1 minus Ti divided by delta t, or equally we can also call this as Ti minus Pti. I want you guys to get used to both of these notations and be comfortable using both of them. Okay, so there's no change. My right hand side, we are going to make some change. My right hand side is d squared t by dx squared, right? So there is also this dispersion coefficient. Okay, now we're going to still use, there is only one way to use finite difference approximation. Okay, so there's nothing much we can do. So we're going to pretty much use the same thing, except we're going to put it as d times ti plus 1 minus 2 ti plus ti minus 1 divided by delta x squared. Now, remember, in your explicit approximation, we used all these variables at the previous time step, okay, at the lth level. Okay, now we are going to use it as a L plus 1 level. Okay. And my right hand side remains the same, so it will be still Ti L plus 1 minus Ti L is equal to by delta t. Okay. So there is really no change here. So the major difference is, in the previous explicit formulation, we used Pti plus 1, Pti, Til plus 1, but now we are Til. Now we are going to use everything at the new time step level. Okay. So if I were to draw a figure here, remember we were always moving from two levels, right? So if I were to draw that diagram, so this is my lth level. L plus 1 level, or this is my PT level, and this is my TI level. Okay, so it will do it both ways. In the previous computational molecule looked something like this. I just drew it actually, remember? To get a node point value here, we use these computational molecules. Okay, so now it's just opposite. Okay, if I want to find the value here, I'm going to actually, let's say here, I'm going to actually use these computational molecules. Okay, I'm going to use L plus 1, Ti plus 1 at L plus 1. These are all at L plus 1. Ti at L plus 1, Ti minus 1 at L plus 1, and Ti at Lth level, okay, or Pti level. Okay. So this is the new computational molecule we are going to use. Okay. Now, so with that in mind, how do we solve this problem? So I'm going to take this thing and define, do some simplification. Well, first of all, I'm going back to the PT notation. So I'm going to remember we're going to use Pti is nothing but Til, and that's the definition, and Til plus 1 is just Ti. Ti will be basically nothing but Ti. So I can write the above equation in that notation as B Ti plus 1, since this is all the new level, so 2 Ti plus Ti minus 1 divided by delta x squared is equal to Ti minus Pti divided by delta t. I'll continue with that notation. Okay, now I'm going to define a term which is nothing but, well, I'm going to basically bring all these terms to here. So I'm going to define d delta t divided by delta x squared times Ti plus 1 to Ti plus 1 is equal to Ti. And I'm going to define this as lambda. Okay, I'm going to just define that. Okay. In fact, we did this very similar definition in the previous derivation too. So once I have that, I can write lambda times Ti plus 1 minus 2 lambda times Ti plus lambda times Ti minus 1 is equal to Ti minus Pti. Okay. So now I'm going to take my Pti to that side, make it positive, and everything else to the other side. Okay, so I'm going to take Pti to my left hand side. So Pti, which becomes positive, is equal to, so this is all going to the other side, so they all become negative. So minus lambda times, I'm going to rearrange the terms, Pi minus 1, okay, plus 1 plus 2 lambda times Ti minus lambda times Ti plus 1. Okay, it's very simple. There's minus 2 lambda, when it went to the other side it became plus, and there is already Pi, so that's where the 1 comes from. So I can write that equation. Okay. So now I'm going to define something. I'm going to call this as well, no, it's too early. Okay, let me cut this off. So I'm going to rearrange this. I'm going to now do other way around. I'm going to flip this whole thing, this to the left hand side and that to the right hand side, and write in the final form minus lambda Pi minus 1 plus 1 plus 2 lambda times Ti minus lambda times Ti plus 1 is equal to Pti. I got a call I need to take. Give me a minute. Hello. It's equal to Pti. Okay. So let me continue the discussion. Okay. Now I can define this minus lambda as A, this as B, this as C, and this thing as D. Okay, so if with that definition I can write this equation as A times Pi minus 1 plus B times Pi plus C times Pi plus 1 equal to D. Okay, where A is equal to minus lambda, B is equal to 1 plus 2 lambda, C is equal to minus lambda, and D is equal to Pti. Okay, so those are the definitions. Okay, so I can define that if I want to. Okay, the cool thing is you can actually calculate these values a priori. How do I calculate it? Let's assume my delta t, some delta t value is 0.1, which you would select, and some delta x value, I don't know, delta x equal to 2. I think that's what we are seeing for the problem, and then some d value. It's again a known value, from which I can calculate lambda. Lambda, remember, lambda is equal to d delta t divided by delta x squared. So this is some number. This is known. Okay, and once that number is known, I can calculate all these guys. So I remember A is equal to just minus lambda. So whatever that number is, okay, I can calculate that, and D is equal to 1 plus 2 lambda. Again, I can calculate that value and put it there. Okay, and C is equal to minus lambda. Okay, and D is equal to Pti. Okay, now what is Pti? Previous temperature, which comes from the initial condition. Okay, so this will come from the initial condition to start with, at least initial condition. Okay, we can get that. So all these are known. Okay, so we can actually assemble these values. Okay, So let's think of how do we actually, now the question is, how do we set up this problem? How do we solve this problem? Okay. It happens that when we actually formulate this problem, this ends up as a matrix problem. Okay, and in fact it is a special class of matrix problem, which will be a tridiagonal problem. Okay, and I'll show you why and how it ends up as a tridiagonal problem. So in order to do that, let's take our standard problem we did so far. Okay, actually you guys did this in the previous homework. Okay, so it was 6-meter rod. 3, 4, 5, 6. Well, it was a 10-centimeter rod. This is x equal to 0, x equal to 10, and we use delta x equal to 2, right? For the problem. Okay. And the node numbers are arranged as 1, 2, 3, 4. So we consider 6 nodes in this problem. Okay. And the boundary conditions are given at x equal to 0. The temperature was given x equal to 0. Oops, x equal to 0. T was, I think, 100 degree, and this is x equal to 10. T is equal to how much was it? 50 degrees. Okay. The initial condition was T equal to 0 everywhere. Okay, so that was the problem we solved. Okay, now once you define a problem like this, obviously from all these delta x and delta t values, I can find lambda, so I can calculate these values a, b, c, and d. So that's known. Okay, so now the question is, how do we get all these matrix equations? Well, to do that, we got to go do it in a very step-by-step fashion. First, let's consider the first node, I equal to 1. Okay, that's known as a boundary node. Okay, that is the BC boundary condition. It's actually BC1 node. Okay. And for that node, I actually know the temperature. So what is the temperature? T1 must be equal to 100 degrees centigrade. That's known. That's known from the boundary condition. So I'm not going to worry about the first node. Okay, so my first node, the issue is resolved. Okay, and I'll tell you how to incorporate that into the matrix in a minute. Okay, so let's consider I equal to 2. So when I equal to 2, I can write this equation. Remember, this is a general expression. So this is the key expression. Still can't draw straight lines, so I apologize for that. But this is an important expression. Okay, that's the expression we are going to use. So from that expression, I can actually write I equal to 2. If I substitute that, I should get A times I equal to 2, so it will be T1, because I equal to 2, 2 minus 1, T1, plus B times Ti, I equal to 2, plus C times Ti equal to 2, so it will be T3 equal to D. Okay. So I can write this equation. Okay. Now, what is D? Well, D is PTI, remember that, right? PTI. Okay. So D is actually PTI, which means, so let me write the value of D. So this is actually PTI, which must be equal to then PR T2. Okay. So now we can actually substitute the values for this thing. Okay, but we're going to just leave it like that. Okay. This is known from the initial condition. Remember that. Known from initial condition. Okay, so we know that. Okay, so we'll leave it like that. Okay, my second node, my third node, I equal to 3. I can write a very similar equation. A times T2 plus B times T3 plus C times T4 is equal to T3. Okay. Similarly, I is equal to 4. Okay. For every node, I can expand and write this equation. A times T3 plus B times T4 plus C times T5 is equal to T4. Okay. And I is equal to 5. I can write A times T4 plus B times T5 plus C times T6 is equal to PT5. Okay. And finally, very last node. Okay. Now remember, last node is an important node. The kind of different node. This is all internal nodes. For every internal node, I can write that equation. For the boundary node, I know the temperature, so I really don't have to do anything. I know the temperature, so just like here, I can write the boundary condition. Okay, so for I equal to 6, it's a special node. It's a boundary, which is called the boundary node. So I equal to 6, I know T6 is equal to, we can also write this equation, but that is not needed because the problem is solved. T6 equal to 50 degrees centigrade. Okay. Now, the cool thing about it is we can take all these. So how many equations we have? We have one equation, 2, 3, 4, 5, and 6. Okay. So we have 6 nodes in the problem, okay, for which we were trying to find the temperature values. 6 nodes in the problem. We got 6 equations. So it's kind of a 6 equation, 6 unknown problem. Although the 2 extreme boundaries are already known, the way in which we formulated is we formulated 6 equations, 6 unknowns, and we should be able to solve it as a linear problem, linear algebraic equation problem. Okay. So if I assemble all this information in a matrix form, this is going to be a little tricky, and I'll do my best. What we get is, so let me try and draw this carefully. So what I would get is a matrix of 1, 0, 0, 0, 0, 0. Okay, this is my first equation. And then a matrix of A, B, C, 0, 0, 0, and 0, A, B, C, 0, 0, 0, 0, 0, B, C, 0, 0, 0, 0, 0, B, C. 5 equation, and my last equation is 0, 0, 0, 0. I'm pretty proud of this matrix. I did a pretty good job here. Okay, which will be multiplied by, I left it up here, T1, T2, T3, T4, T5, T6, which is equal to T1, T2, T3, T4, T5, T6. Okay. So now these are boundary conditions. These 2 will be boundary conditions. BC1, both the boundary conditions will sit here, and these are initially start from the initial condition, and then they'll keep updating. So this matrix equation is exactly same as writing those 6 explicit equations. Okay, why? Because let's look at the first equation. I take the first row and multiply by this. So remember, matrix multiplication operates this way, right? Okay. Everything is 0 except T1. So what I got is T1 is PT1, which is equation number 1. The second equation is A times T1, B times T2, C times T3 is equal to PT2, which is my second equation. Third equation is A times T2, B times T3, C times T4 is PT3, which is my third equation, and so on. So we basically put this 6 equation, 6 unknown problem into a matrix problem, and this is also, as I said, it's a special type of matrix problem, because what you have is entries in this matrix are only along the diagonal. So carefully look at it. So that is my diagonal. Okay, my diagonal has got C's. Okay, and my sub diagonal basically has C's. My diagonal has got B's, sorry. So this is, remember, this is 1. And my other diagonal has got A's. Okay. So there are only 3 and everywhere else is 0. So what we have is a matrix which consists of a bunch of B's in the middle. Okay. I got a very special form of matrix, which is essentially it's a 1 here, and B's here, and then C's here, A's here. Okay. Everywhere else, everything is 0. Okay. So it's a tridiagonal matrix. Okay. And we know how to solve tridiagonal matrix because we already solved one. Okay. So the way to assemble it is basically from the problem. When you write actually a computer program, the first thing you do is you actually compute it. So how to write a computer program? When you write the computer program, you basically assemble these A matrices. Okay, so you assemble this A vectors, B vectors, C vectors, and D vectors. Okay? And D vectors come from PT values. Okay. Now A, B, C, D are basically defined from the previous definitions. Remember, right? So we already defined A is A. All the entries of A will be basically minus lambda. A's will be minus lambda. Okay, and B's will be 1 plus 2 lambda. Okay, and C's will be minus lambda. Okay. We can calculate lambda because lambda is, once you know delta x, delta t, and d, that lambda can be explicitly computed. Okay, so all the matrices can be filled. Okay, and interestingly, you will find that the diagonal matrix B will have at the very beginning it will have actually a 1 here. Okay, 1 0 0 0 existing. Okay. By the way, I made a mistake here. Okay, I should have actually, the very last equation is what? T6 equal to 50. I just noticed that. Let me correct that. Remember, the T6 equal to 50, right? So, let me correct that. So this cannot be A. You see that? Okay, that's not an internal node. So let me go back and grab this. This will still be 0 and this will be 1. Then only you can say T1 0. When you multiply, T6 equal to PT6 will be 50. Remember that. This will be 50. And that will recover this equation. Okay, so you can't put A and a B here. Okay, so that's a mistake. Make a note of that. Okay. So when you actually assemble this matrices, the very first entry in the B matrix will be 1. Very last entry will be 1. Everywhere else it will be this 1 plus 2 lambda. Similarly, the A matrix is assembled such a way that it will be a constant minus lambda everywhere, and the very last entry will be 0. Actually, the very first entry also will be 0. Similarly, the C matrix, the very first entry will be 0, and then we'll keep assembling it until C everywhere else. Okay. So I given a template of a computer program for this. Okay, and you can actually use the computer program and see how I am assembling it, and you will see the logic what I talked about. Okay, and once you actually assemble the matrix, you then call the tridiagonal solver that will solve for T1, T2, T3, and T4, and then you got a delta T solved. Okay, and then once you got the new temperatures, then you can transfer them to the old temperature and go to the next time curve, just like how you did in the explicit method, and you can then repeat the process again and again to solve this problem. Okay, so that's how you would develop an implicit code. Implicit codes do not have any stability criteria. The advantage of implicit code is advantage. So why are we doing all this? The advantage of implicit code is it's unconditionally stable. Okay, they are stable. They are. And one of your homework problem is to actually take the previous homework problem and show it will indeed be stable. Okay, so I'll stop here and we'll continue this discussion in the next lecture.